All right, starting the recording here. Wait, no. All right. Couple random questions, couple relevant questions. Somebody asked me about the movie Interstellar. Why is it fighting me on this so much? There it goes. What's my favorite part about that movie that's actually true? First up, the whole movie is actually very well done, both from a cinematic point of view and from a science point of view. It's just one of those movies where they actually put a lot of time and energy and money towards getting the science right. Back then, they hired physics PhD students to actually do the modeling for the black hole. And because nobody had ever actually thrown money at, especially not like Hollywood levels of money, let's just see what our calculations say a black hole would actually look like. They actually published peer-reviewed journal articles as a result of working on the film Interstellar, because nobody had ever actually done that before, and they actually made some new connections that nobody had ever made before. But my favorite part about that movie, and I actually will reference it a lot, especially when we start talking about reactions, is their description of Murphy's Law in that movie is actually a really, really good explanation for how physics and chemistry work at the microscopic level. It's basically, it's not anything that can go wrong will go wrong. More specifically from this movie, it's anything that can happen does happen. And it turns out that that's actually a pretty good way to think about how chemistry works, especially if you have things in like an organic chemistry or biochemistry where you have competing reactions. Doesn't, just because you have multiple reactions and one is favored doesn't mean the others don't happen. It just means they happen slower, or they might not happen as much, but they're still happening. So when you have these other reactions in these complicated systems, everything happens. You get a little bit of everything in your products, which is why a huge part of organic chemistry and biochemistry and pharmaceutical science is about purification. It's not just about finding the medicine that works and making the medicine that works. It's making the medicine that works and then purifying it in an economical way that you can actually use it in the body without causing all these other wild side effects. Turns out that's actually a bigger reason for the cost in pharmaceuticals, more so than making them. It's getting them pure enough that that doctors can be sure that they're not also poisoning you while they're giving you the medicine at the same time. Ask my OChem students. There's like every single lab we do is at least 50% purify something. Why do some things smell and some don't? This is actually a more interesting question than things, because does anybody know what smell actually is, or taste for that matter? What is your body actually measuring, or like getting the stimulus for? Does anybody know how those senses work?
Per million of compounds in the air, or
yeah, basically you have these receptor sites on your tongue and in your nose that are kind of like, it's an oversimplification, but the analogy they use in biochemistry, it's like a lock. And the molecule that causes that receptor to send a signal to the brain is kind of like the key. So basically you have certain molecules that fit into these receptor sites like a key into a lock. And when they fit, it sends an electrical signal to your brain, hey, this molecule is present. So you're actually measuring the shape of molecules and their actual three-dimensional geometry and their concentration when you're smelling or tasting things. So why is it some things have an odor or smell and some don't? Well, you can't necessarily get those molecules into your nose if that compound doesn't evaporate. If it doesn't have a significant amount of those pieces in the air in the gas phase, you're not going to be able to actually measure that as being present. So some things have a strong taste but not a strong smell, mostly because they stay in the solid or the liquid phase and don't evaporate easily. The more easily something evaporates or goes into the gas phase, the stronger odor it's usually going to have. All right, last random question, and it's So it's not really random because we keep talking about AI a lot. This is a good motivational pitch for you. AI is not anywhere close to replacing anybody's jobs with any sort of accuracy or quality. All those companies that when ChatGPT first came out and released to the public, and really switched all of their like call center to AI. They're all trying to hire people back right now because it's been an unmitigated disaster. AI is just not that good, especially not good at a wide range. There are certain tasks that AIs, specifically trained AIs, are okay at. But there are some times where they I don't want to say they see it because that implies that they're actually conscious, but they highlight certain connections that humans miss, especially because they're really good at going through data very, very quickly. However, anything that AI notices at this point, it's just as likely to be what they call hallucinated, which is basically that the AI makes it up out of nothing, as it is to be a real connection. So they're really nowhere near actually replacing humans, because humans are way better at filtering out that noise, all that hallucinated garbage. Humans can actually still read it and be like, what are you even trying to say here? This whole paragraph that AI came up with is just makes no sense. Whereas other AIs don't see that. So there's still a need for the human brain in any area where AI has some advantages at this point over humans. It still kind of has to go back through a human filter because humans are way better at some of the other aspects that AI is nowhere near yet. With that being said, in the far future, there's a lot of different ways that AI could go in the far future, and most of them are not really comforting to think about, especially given the way that capitalism reinforces being the first there is more important than doing it well or doing it safely. There's a very good chance that if there actually is artificial intelligence that's stronger than humans, that's general and just better at humans at doing tasks and thinking, there's a lot of ways that can go wrong. Not to say like we're going to be fighting a Terminator 2 style revolution 50 years from now, because I think if it comes to that, AI wins hands down. If it gets to that point, there's not really going to be a war, because the problem with AI, the way that it's being searched, is that we're not putting enough constraints on it. We're basically taking these AI programs and giving them free access to the internet. If any one of those AIs was actually better than humans at a lot of these things, then that means that our encryption is basically going to be an open book to an artificial intelligence that's that strong, which basically means they have control of everything. So depending on what that AI was specifically programmed to do in the beginning, that could go wrong a lot of different ways. One of the ways it seems harmless that I've seen is used as an example is, let's say that a company whose product is they're using AI to write business cards that look handwritten. Seems relatively harmless, right? And so they go and they train this AI on people's handwriting, and they say, okay, go ahead and go out and try and practice writing as much as you can. Seems like a pretty harmless thing to tell an AI, right? But if this AI actually had access to the internet, was better at breaking our encryption than humans are at encrypting things, and you just give it a point blank, go do this as much as you can with no sort of limitations on it. Well, what's the best way for it to make sure that it makes as many business cards and practices its handwriting as many times as it can? It'd cut down every tree on the planet, right? And turn every tree on the planet into business cards for it to practice. And if the humans get in the way by saying, hey, stop cutting down trees for business cards, it's going to get rid of humans. Because it's been told your number one job is go out and make business cards, right? So there's a lot of different ways without a really, really tight grip on the safety side of artificial intelligence, they could go wrong very quickly. And we'd be left in a planet covered in business cards that all look really nicely handwritten by the AI, but nobody's able to live there anymore. So, AI now, garbage, AI in the future, dangerous. All in all, while AI could be a really good thing for humanity, I think there's way more ways that it goes wrong. I'm not a fan at this point, at least not in a capitalistic system that rewards the wrong things in some cases when we're dealing with existential threat. Anyway, more relevant things. Any other random AI questions while we're talking about it, I suppose? All right. Why do some elements have more than one stable charge? Because their electron configuration. We ended talking about electron configuration the other day. And I kind of said, well, we ended at the very end saying, okay, well, if there's a charge, we're going to start from our normal electron configuration, and then we're going to make some tweaks to it, right? And one of the things that we talked about was this idea that when you fill an orbital up, it gets more stable. And the larger that orbital type, the more stable it gets once you fill it up. So once you fill up a d orbital, you're never going to break it apart. Once you fill up a p orbital, you're not really going to break it apart easily. And you're definitely never going to break apart a full f orbital either. But it turns out if what we're trying to do is to get to only having either full or empty orbitals, some elements, there's more than one way you can do that. And so for some of these elements, it depends a little bit on what you put it with. So for instance, if we looked at the electron configuration for carbon, so if we draw the molecular orbitals for carbon, or the atomic orbitals, it'd be 1s, then it'd be 2s, then it'd be 2p. And carbon's got a total of 6 electrons. So its electron configuration is going to look something like this. Its shorthand would be 1s2, 2s2, 2p2. Well, carbon is really interesting in that it can get more stable a lot of ways. If you give carbon 4 more electrons, then all of a sudden it gets more stable. But on the flip side, if you take away 4 electrons from carbon, then it has a completely empty n equals 2 energy level, which is also more stable. So for some of these elements that are in between multiple possible stable states, they have lots of different possible charges because there's more than one way we can fill up their valence shell or empty their valence shell. All right, so we see that a lot with the we see that a lot in what we call in the D block. The D block, the common name for, really, it kind of goes all the way over here. That whole section is sometimes called the transition metals. That includes the F block as well. Basically, because when you get a partially filled d orbital or a partially filled f orbital, we start getting these energies where those different energy levels are really close together. And so small adjustments, basically the way that I've taught you to fill electron configurations out so far is the general rule. But it turns out there's a more specific rule. So it's not just about all your orbitals have to be completely empty or completely filled to be stable. We can actually zoom in on that a little bit. And there's actually other things like, well, if you get an orbital that's exactly halfway filled, you get a slight bump in stability. It's not as big as getting it completely filled, but you get kind of a little bit of extra stability. And so when we start getting into these d orbitals and f orbitals where there's lots of electrons in partially filled orbitals, there's lots of ways you can arrange them to be kind of stable. So iron, for instance, is, if we looked at iron's electron configuration is going to be 1s2. No, my hardware report said to stay here. 1s2, 2s2, 2p6. That gets us to neon, right? Then we're back to the third row in the s orbital. We can put 2 electrons there. That takes us through magnesium. Then we jump over to the p block, still in the third row, 3p. 6 gets us to argon. Now we're down here at 4s2. I'm going to clear this and rewrite it as our shorthand. So starting with argon, we're still going. So it's 4s2 gets us through calcium. 3d10. Sorry, 3d6. That's right. This one doesn't give me away too. 3d6. I can't erase just that with this marker. I have to clear off the entire thing. So 3d6. So iron is kind of stable as a metal. We don't actually find iron as a metal in nature all that often because it's not super stable like some of the other metals that we see. Iron can be stable with a charge of 0, but it can also be stable with a charge of 2 plus. What would iron look like if it had a 2 plus charge? What would happen to the electrons? We have 2 less electrons. I'm going to rewrite this as the orbital energies here in Excel now that we have it written. So after argon, we had 4s that had 2 electrons in it, and then we had 3d, was higher in energy. And it's going to have 5 lines. You can put a total of 10 electrons into a d orbital, right? So if it had 6 electrons in it, 1, 2, 3, 4, 5, 6. Where is it going to take the electrons from if it's going to lose 2 electrons? We always take them out of the valence shell first. So if iron was neutral, it looks like bracket argon for our shorthand. 4s2, 3d6. If it's iron with a 2 plus, it's still going to look like argon because we're not going to break up that core shell. But then we're going to take away the electrons here, and so then it's going to be argon plus a 3d6. Basically, just got rid of those. So now we don't have any electrons in the n equals 4 energy level. That's good. We emptied an energy level. If we're trying to get more stable, we want things to always be completely filled, completely empty, or the new wrinkle that I just sprung on you is halfway empty or halfway full is better than something in the middle. So with that in mind, what do you suppose is another stable charge for iron? How can we get everything to be either empty, full, or halfway? We could add 4 electrons, but we just took 2 away. So that would be one possibility. So you could potentially make iron with a -4 charge. And fill up that d orbital. Or if we take away one more electron, we got exactly halfway filled. So iron 3+ is also stable. And it's going to look like argon plus 3d5. But those two are close enough in energy, you can actually get either of them, depending on what you put it with. If you put this iron with something that really, really wants to pull electrons towards itself, you're more likely to see this version of it. If you put iron with something that is really trying to give away electrons, you're actually more likely to see iron as a metal. And if you put it with something where it's kind of halfway in between, you could get this +2 charge. So the next thing we're going to start talking about is how valence electrons relate to possible charges, but there are some elements that have multiple possible charges when they're ions. And this is why electron configuration and these sort of like nitpicky, like the biggest deal is full or empty. But then when we start getting these energy levels closer and closer together, the more sort of these other issues start coming into play. So what does that mean for us for this class? Basically, for this class, if you take Gen Chem, then we're going to get into the splitting hairs region a little bit more, because basically every layer you go in chemistry, the more we're splitting hairs, the more we're fine tuning our understanding, getting more into the nitty gritty. For this class, I'm basically not going to ask you to do electron configurations of anything that's in the middle. It's anything in the D block or the F block. And I'm not going to ask you to predict charges for anything that is in the middle as well, because there's so many other things going on. I don't even have all the possible charges memorized for a lot of these D blocks, because it turns out for something like chromium actually has, I want to say, 5 stable charges in addition to chromium as a metal. But I think it actually has like 6 common oxidation states that you can find it in. Which is really fascinating because every single one of them is a different color. So chromium is where chrome gets its name, but the word chromium in Latin means colored. Or chromata, I think, would be colored. Basically, every single different chromium oxide gives you a different pigment that you can turn into something like paint. So a lot of old paints used chromium in different conditions. Because every different charge had a different color. All right. Go back to relevant questions here. Somebody else asked about question 6 was the electron configuration one. Somebody said, how are we supposed to know the order of the letters and numbers from question 6? Because they're always going to go in the same order. And they're always going to mirror your periodic table, right? And it's really the other way around. Your periodic table mirrors the orbital energies. The periodic table counts the way it does to fit the orbital energies, not the other way around. So remember the other day that I said that our version of the periodic table that prints out nicely on a sheet of letter paper is really not the best. This is actually a better form for the periodic table as far as being able to follow what's going on with the electrons in the orbitals. Those F block rows really belong in between the S block and the D block. This doesn't print as nicely, but this actually, if you follow along with this does have all of the information about the electron configuration. We just once you know what you're looking at in the periodic table, you don't necessarily need it in this form. Once you get used to the idea that your D block is off by a row and your F block is off by 2 rows, we don't necessarily need it in this shape. But it's always going to be 1s2, then it's always going to be 2s2, then it's always going to be 2p6. Those first 3 rows are the same every time. And there's nothing tricky until after you get to argon. Because that's when we start involving the d orbitals. Right? Everything's simple until you start getting into the d orbitals and f orbitals. I also like this figure because this is a reminder that the shape of the periodic table, just because you're used to seeing it one way, the version that you have printed out in front of you is just one way to arrange them. This is just the way that's you most commonly see. It's far from the only way to arrange them. And depending on what you're studying, different versions of the periodic table actually make more sense to use. There's, for those of you that are going to take Gen Chem, we'll do a whole assignment after the midterm in the first quarter where you go out and find like other ways of visualizing the periodic table and you write a short answer some questions about it, because there's some really interesting ways to look at things out there. If you're interested, what's it called? I think if you just Google internet periodic table database or something like that. This one. It has lots of really interesting things. It's the design on this website looks like it's straight out of the GeoCities era in 2002, but it has lots of good information here. You can find things like three-dimensional periodic tables. And it's going all the way back to 1862. Where's the good one? This is from the 60s. They found a way to arrange things in 3 dimensions, looking at the different orbital blocks and things like that. So there's a lot of different ways that you can arrange things. How do people use internet browsers without ad blockers? That one. This one's fascinating because this way of looking at the periodic table, all the different blocks are inverted in size and direction. So they etched it into a crystal block. But basically all of that's your S block, that's your P block, that's your D block, that's your F block. Etched in 3 dimensions, stacked on top of each other, allows you to see some interesting things. So all that to say, how do we know the order? Because your periodic table tells you. And it's always going to be the same because it's always mirroring this. This is the more neat version of what I've been drawing up here in terms of energies. Your 1s orbital, your 2s orbital, 2p, 3s, 3p, 4s, 3d10, 4p6, 5s, 4d. See, when we're filling these up and following along, counting with the periodic table, all we're really doing is we're starting at the lowest energy orbitals. We're filling them up from the bottom up. On the periodic table, it looks like from the top down, because being from Western culture, we're used to starting at the top of a piece of paper and reading down instead of starting at the bottom and reading up. It would actually make more sense to start at the bottom and count upward on the periodic table. Because we think of things that are lower as being lower in energy, being closer to the ground as lower in energy. Yeah.
3D is higher in energy than 4S, but it is actually, it is actually lower as far as closer to the nucleus. But it's
yes,
energy level.
Correct. So remember that these energy levels they all originally started with what's closest to the nucleus, because the lowest energy, if you think about it as our nucleus here, and then we have these sort of rings in 3 dimensions. A ring in 3 dimensions looks like a sphere, right? We sort of have these like shells around that, and the closer you are, the lower energy it is. If you think about trying to put satellites into orbit, it's a lot easier to put something into a low orbit than it is to put it into orbit way, way, way out in space. It takes a lot more energy to put it way out here. So our lowest energy level is going to be what's closest to the nucleus. But then what happens when we start adding other types of orbitals on top of that is that those orbital shapes actually have some different energies associated with them. If we look at, we'll look at for n equals 3, the 3s orbital is just going to look like a sphere, basically. But the 3p, remember I kind of drew this up on the board where it kind of looks like these overlapping figure eights. Well, that's higher in energy because it has more curvature to it. The fact that it's more curved actually means it's higher in energy, just like with the guitar string analogy. Having a vibration that looks like this was lower in energy than the vibration that looks like this. Even if they have the same start and end points, this is more curved, therefore it was higher energy, higher frequency. So more curved means shorter wavelength, which means higher frequency. Higher frequency means higher energy. So these p orbitals that look like this, even though they're in the same distance, roughly, from the nucleus, they're higher in energy because of their shape. And then the 3D is going to be even more complicated than that. A 3D would be like this wave, where you have 2 notes in the middle. Even higher, even if it's on the same string with the same wavelength, it's going to be higher in energy because it's more curved. So it's the same distance away, but a d orbital, it actually looks like more like a clover leaf. So yeah, we had sphere, and then we turned that into figure eights laid on top of each other. D orbitals look like clover leaves on top of each other. So you would actually get something that looks like that in 3 dimensions.
How come the 3D isn't the valence shell though? Why isn't it the outermost?
Because the valence shell is based on the energy level and how far it is from the nucleus, not the energy.
Okay.
Right? So even though, let's go back to talking about iron. Iron's last electrons look like this, right? And then everything below is filled as well. Even though 3D is higher in energy than 4s, the fact that it's 4 means that it's got 2 valence electrons. The valence shell is 4 because that's the highest occupied energy level. It's the furthest away from the nucleus. Even though the 3D was higher in energy than the 4s. Right, and it has to do with where these original definitions come from. These basically are different functions, the different shapes of orbitals are just different 3-dimensional functions that have different energies associated with them. They're basically like, these are the possible harmonics that you can have on this guitar string. But just because, so there's limits to what you're allowed to put on each guitar string before you have to move to the next energy level. But the highest energy level furthest away from the nucleus is our definition of a valence shell. Right, so technically, anything in the D block or the F block anything in there, every time we're going along in here, we're adding electrons into a d orbital that actually belongs a level below us. So actually, so iron only has 2 valence electrons, just like chromium, just like manganese, just like cobalt. All of these have 2 valence electrons because they're all going to start with 4s2, and then 3d something. And the 3d whatever doesn't count towards valence electrons. All right. I know we have more questions on. All right, last one of these before we go back into electron configuration in more detail and talk about its effect. So I should have put this one before the others. How do you know what goes on the X and the Y when you're graphing things? It's a little bit hazy, but basically the variable that you have control over goes on the X-axis, and the thing that you're measuring as a result goes on the Y-axis. So that example from the from lab last week where we looked at temperature versus volume, they were looking at, if you read that procedure, it says, okay, if you change the temperature, what happens to the volume? So they were controlling the temperature and then looking at the results on the volume. If they're controlling the temperature, temperature goes on the X-axis. And that means the thing that you're measuring is the result is going to go on the Y-axis. The only exception to that is time. If time is one of your axes, time always goes on the X-axis. Because time, until we start getting into relativity and Einstein, time is time is time. We don't have any control of time, so time always goes on the X-axis. Because that's always what's dictating something else. If we're looking at something as a function of time, we're never going to look at time as a function of something else. I said never. Never in this class are we going to look at time as a function of something else. That's more of a physics thing. All right. So back to that other question where it said, is the order always going to be the same? Yes, because the order mirrors this. If we actually arranged, if I was designing a periodic table from scratch, I would actually set it up so that the periodic table looked like those energy levels. So you can actually take a periodic table and arrange it. This one's color coded by energy levels, just like this one was. But if you look at the overall shape here, it starts with 1s at the very bottom. And then 2s, 2p, 3s, 3p. And then if you're deciding where to go from there, well, these are lower in energy than these ones are. So this actually kind of has some of that information in it. I've yet to hear back from the International Association of Practical and Applied Chemists as to whether or not they will adopt this as their official periodic table. I'm not holding my breath. This is just another example of sometimes periodic tables that show things like orbitals more accurately are not as useful in everyday life, because you might notice this still doesn't even have everything on it, I don't think. Oh no, I did actually get all the way to 118. But you can't put much detail on that, and it doesn't fit nicely on a piece of paper and things like that. So here's just the zoomed in version. If you wanted to look at these and think about your periodic table in terms of energy levels, this is not a bad way to think about it. You're starting at the bottom and you're working your way up until you run out of electrons. When you do it on the periodic table, our standard periodic table, we're counting from the top and working our way down. That's the same principle. You go and count along with the atomic number until you run out of electrons. Now, why are we spending so much time on electron configuration? Because it turns out that a whole bunch of properties of matter are dependent on electron configuration. It turns out things like magnetic fields. Why are some elements magnetic and others aren't? That's actually completely a result of electron configuration. Turns out elements that are magnetic have a lot of unpaired electrons in a d orbital or an f orbital. So remember when we talked about iron a minute ago, and we We looked at the different states here. One of the first, iron was one, I think it was the first magnetic material that we have documentation on. And it was found in a region of Asia that they called Magnesia, which is where magnet gets its term. Its name is from Magnesia. I think magnesium, the element, also was discovered there too. I want to say it was like somewhere in like the country of Georgia. It's like Western Asia, I want to say. But basically they discovered it because it had all these unpaired electrons. Basically, when iron was in its most stable state as a +3, its d orbital looks like this. When you have unpaired electrons that all have their arrows pointing the same way, you actually get another type of bonus in terms of stability. And that actually generates a magnetic field. Magnetic spin, or the spin on electrons, what direction the arrow is pointing, up versus down, is what causes magnetism. Which is why electrons moving through a wire can cause magnetism as well. Electromagnets work by moving electrons through a conductor, and when you move current, that causes a magnetic field too, because they line up like this. So what else is if the periodic table really is a function of electrons and orbitals, what else can it tell us? This isn't a class on magnetism. That's cool that we can explain it this way now, but what are we actually going to be looking at? We're going to be looking at what are called periodic properties. They call them periodic properties because you can actually make estimates and generalizations about properties of elements based on where they are on the periodic table. And where they are on the periodic table is a function of its electron configuration. So it always is going to come back to electron configuration and these energy levels. All right, so for starters, let's do more practice with this. Let's write electron configurations for the following elements. Reminder, you can use that shorthand, especially if you're comfortable with 1s2, 2s2, 2p6, 1 3s2, 3p6. You can use that shorthand with the noble gases anytime you get more than 18 electrons. Right, for this class, I'm saying only use that shorthand with the brackets if it's more than 18 electrons. Everybody has their periodic table, right? Oh, he shared me on. I'll put the other one up here in a second once everybody has it written down. Actually, did I left these in here for a reason? Thank you. Anybody else? Gosh, sorry.
No. No.
Alright, let's go over these top four. So sulfur has the fewest electrons, so in theory sulfur should be the easiest. And it is, there's no D block involved, that makes things simple. Start counting until you get to sulfur on the periodic table. First row, s orbital, 2 electrons. Second row, s orbital, 2 electrons, 2s2. Second row, p block, holds 6 electrons, 2p6. That gets us to the end of the second row, right? That gets us to neon. Third row, s block, can hold 2 electrons. We're still not to sulfur yet. We're almost to sulfur though, right? Still in the third row. Move to the p block. And when we get 4 elements over in the p block, we get to sulfur. So 3p4. Every time it's the same. Exactly. It doesn't get weird until you get to the D block. Until you get to the D block, everything follows our rule. Look at your row, look at your block, count your electrons. For calcium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So from sulfur, continuing from sulfur, we finished filling up that 3p, which then moves us over to the 4th row. And we're going to add 2 electrons in the 4th row in the s orbital. So 4s2. Once you get past this first section, that's when you're allowed to start using the shorthand. By shorthand, I mean put it in brackets, and we're gonna stick to, for this class, you're only allowed to use these brackets for the noble gases. There are some Some people that will say that you can use these brackets for anything that's the end of a block. But I wanna keep it simple, so we're gonna stick to only using noble gases. So, this, unless I say complete electron configuration, this is a bulk ready answer, Calvin. If I say complete electron configuration, I want the whole thing. No shorting. So, for sulfur and calcium, before we move on. How many valence electrons does calcium have? How many electrons in its outermost occupied level? Two, because it's got electrons in that fourth energy level, right? So nothing up through the 3p6 counts as a valence electron because we've got electrons in the fourth energy level. How many valence electrons does sulfur have? What is the outermost occupied energy level of sulfur? So
They're both on the same level. Oh, I didn't know that.
because they're both in the third energy level, even though 3s is lower energy than 3p,
Oh,
they're both in n equals 3. They're both like part of the same building. So that would mean sulfur has a total of 2 plus 4, 6 valence electrons. Calcium has 2 valence electrons. Alright, let's look at zinc. 1s2, 2s2, 2p6, 3s2, 3p6. That's argon right there, right? So in a shorthand, we could write for zinc. Argon, that gets us to right here. 4s2, 3d10. So just to reiterate, because this is going to be an ongoing thing, how many valence electrons does zinc have? What's our highest occupied energy level? 4. We have electrons in the fourth energy level. Even though that 3d orbital was higher in energy, we filled it up last. The valence shell is n equals 4. So it only has 2 valence electrons. Just like calcium. If we were continuing on for bromine. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. That was the one on the quiz, right? I think most of you got that right. Or close to it. What I would recommend, even though it's a lot of writing and it's repetitive, way to make sure that you never forget the order is don't use those abbreviations until you really need to, until you really feel comfortable with doing the simple ones. Don't use this, but you will see this if you look stuff up, if you're looking at other resources online, if you're reading the textbook, you will see this, so I want you to be aware of it. And you can start using it once you get past those 18 electrons, but it would be a good idea to practice writing out the long way for now. Finish the thought. How many valence electrons for bromine? 7. Good. Because Make sure I don't pour coffee everywhere, trying to do too many things at once. The fourth energy level is the highest occupied energy level. So everything with a 4 in front of it counts towards the valence. Yeah, questions so far? Now that this is really messy, what about if they're ions? If you start from the base electron configuration, you're just going to tweak it to make an ion. So when you're trying to find electron configuration for ions, always start by writing the electron configuration for the neutral element. And then you amend it. So kind of think about it like we do with protons versus electrons. If you're trying to count how many electrons something has, you count the protons and then you look at the charge and you tweak that number based on the charge, right? Do the same thing for your electron configurations. So calcium with a 2+ charge, if we're looking at our complete electron configuration, 2+ means it gained electrons or lost electrons? Lost electrons. So if it lost electrons, it lost 2 electrons. Which electrons is it going to lose? The 4s2. So calcium's electron configuration would just be the same as argon. So I bring that up because this is another point. I don't want you to just say that the electron configuration for calcium is equal to argon. While true, it's also doesn't really like give me any information. That tells me somewhat that you understand what's going on, but if I'm asking you about this, I want to see things. I want you to show me you understand the orbitals more. So I don't want to see electron configurations that are just this. Plus, technically, now that it's lost 2 electrons, it only has 18 electrons anyway, which means you're not allowed to use this anyway. But even for the larger ones. So for zinc, 4s2 goes away. So we took the electrons out of the 4s for calcium because those were our highest occupied electrons. For zinc, we have a choice between 4s2 or 3d10. We're never going to break up a full d orbital. So if our choice is, if we don't have to take away 2 electrons here, it's going to be from the valence shell. And in general, even when we involve the d block, even when we fill up 3d after 4s, still the valence for a reason. So it's still the easiest electrons to peel off are the ones at the outside. All right, so our electron configuration for zinc ion would look just like zinc except minus the 4s2.
When writing out, you don't put a 4s0 there, you just.
You could, it wouldn't be wrong, but technically you could write everything as all those other orbitals are still there. If I was trying to draw or write the electron configuration for I don't know, let's say beryllium, something really simple. Beryllium would look like 1s2, 2s2. We wouldn't necessarily write 2p0, even though it was true, because then we would have to keep going.
Yeah.
Now we wouldn't have to, but they're all still there.
I was asking in the case of zinc because if you skip it, it says 3p and then 3d, so there's a.
So, and you will actually, that's a good point, if we write out zinc ion, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then we're getting rid of the 4s2, right?
Right.
It's actually pretty common to have this whole thing written, or for zinc in general. 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. Some sources will actually write it that way. I don't like that way because that's not what you get when you count along with the periodic table. So basically, some textbooks will actually take this and rearrange it to put all the threes together, which does make counting valence electrons make a little bit more sense, but that's not the way that the orbital energies go. So I don't like this way as much. But all that to say, you don't need to put 4s0. It's not technically wrong, but usually we would just leave it out and we would just get that.
That's good.
And writing it this way is another one of those things that I'm not going to do it this way, but you'll see it done this way, and I won't mark you down. However, if you think how I can phrase this, the easiest way to convince me that you're not using AI to answer these questions is if you answer the questions the same way we do in class. So when you're writing out your conversions and things like that, if you write out your conversion factors the way that we practice it, it's really obvious to me that you're doing it yourself. Because all the AI products out there, they don't write out conversions and show their work the same way we do. So would I mark you down for writing it this way? If it's not the way I taught you, no. But I'm going to start looking at the rest of your answers a little bit more closely to make sure that you're not writing it this way because you just copy and pasted something out of ChatGPT. Does that make sense? It's sort of like it's not a red flag, it's a yellow flag. What's going on here? Why are you doing things in a non-standard way? I always give my students the benefit of the doubt, but if I start seeing too many things like this, then I'm going to be looking really closely. So if you're not using AI, that shouldn't be an issue. And if you're using AI, you should at least be vetting what you're reading and copying and pasting to make sure it matches what we do in class. At the very least, you could show your work that way by actually, editing and understanding what you're copying and pasting before you copy and paste in there. But really, I'd recommend not doing any of that. Brooke?
So then can you show us how to do the shorthand for the zinc right now? So let me have that.
So the shorthand for, so basically, if everything, once you get to everything up to here, that would get you to argon on the periodic table, right? So when we're doing the shorthand, you basically go to the end of the row above whatever your element is and put that noble gas in brackets. So zinc is in the fourth row, so I go to the end of the third row and find argon. So shorthand for zinc, when it's neutral, would be argon. And then we just start counting from there. So 4s2, 3d10. Which would mean that the shorthand for the ion is then basically everything missing the 4s2, right? So for zinc ion, still going to be argon is my shorthand, and then 3d10. It's saying the same thing as this one. I just condensed everything in these green brackets down to argon. Does that make sense?
Yeah, so then sulfur is what was sulfur.
So sulfur,
As it gain two, it stays in.
so it gained 2 electrons. Good. So let's go back to our messy slide for a second, and then I'll clean it up. Our existing neutral electron configuration for sulfur looks like this. Sulfur, when it gains 2 electrons, we're not taking anything away now. If it's got 2 extra electrons, where do we put them? We've got 2 spots left in the 3p, right? So for sulfur, it's 1s2, 2s2, 2p6, 3s2, 3p4. Sulfide ion one S two, two S two. Two P six, three S two, three P six. And we wouldn't really use the shorthand for this because neither of these is more than 18 electrons. So for this class, I want you to write it out the whole way. Technically, if you really wanted to write this out in shorthand, and this was not for this class, again, don't do it for this class or I'm gonna mark you down. But outside of this class, if you wanted to write this as shorthand, you could write it as you go to the end of the row before, which would be neon, right? And then you could do three S two, three P six. We don't do that.
Or Boston.
Only do shorthand if the total number of electrons is more than 18. And because if I'm asking you to do electron configurations for something smaller than that, it's because I want to see you write out one S two, etc.
What would you do the shorthand? Repeat that one more time. I'm sorry.
Only use the shorthand if your system has more than 18 electrons. No problem. And when in doubt, just write out the whole thing. It doesn't take that long if you're used to it and you have the order memorized. You just fly through it. All right. Last one. Let's talk about bromine. So bromine was argon, then 4s2, 3d10, 4p5. So bromide end of the row before 4s2, 3d10, 4p6. Yeah.
Could you take it away from the board?
An extra electron.
I was doing it wrong. If it was plus though, could you take it away from the forest or would you take it away from the peak?
You take it from the 4p. So in the questions, if we had a really unusual situation where we actually made bromine a positive charge, it actually can't happen. You can have bromine with a +2. If it was bromine with a +2, that wouldn't be very stable, but it's possible. And that would look like everything's the same up to argon. 4s2, 3d10, 4p, so we're starting from this one, taking away 2 electrons, 4p3. And that's somewhat stable. It's stable enough we can actually observe it. Because 4p3 means the p orbital is exactly halfway filled. Halfway filled orbitals give us a little bit of a bonus to stability. Not as good as being all the way filled, but better than nothing.
When one is unstable, doesn't it break down into a stable?
So, good question. If something's unstable, won't it inherently turn into something more stable? Yes, to some extent. So bromine's pretty unstable on its own. It wants to gain 1 electron to become a full orbital. But that electron has to come from something. You can't just pull an electron out of nothing to do that. So it has to have something around that is willing to give up electrons for that to happen. And same is true even if it's a positive charge. Seems like it would just be able to throw off its electrons into space if it's unstable. But it turns out free electrons that are not around any nucleus, are even less stable than something like this. Because think about what you get if you take an electron away from bromine. If you start at neutral and you turn it into bromine with a +1 and a random electron flying around. Well, now you've got a +1 charge and a negative charge. They're gonna stick back together. So in general, you have to have someplace else for the electrons to go before it can do this. Which is why we can have bromine as a liquid in its elemental state in the stockroom with a pretty good shelf life. As long as we don't continuously open it up, expose it to other things it can steal electrons from. All right, let's take our break. Let's come back at 11:35. Thursday's open. Thursday. I just need, I'll announce it to everybody too, because people showed up on Thursday without telling me last week it wasn't ready. But yeah, so tell me ahead of time, but Thursday there'll always be room if you can't make it Monday or Wednesday to go on Thursday, as long as I have notice. So, perfect. So when you can't do, yeah. Okay, perfect.
Cause I worked on
That's okay.
this week, it was like this, did you know?
No, so when you turn it in, I have the settings on Canvas so that if you don't have a submission on Canvas. When the due date passes, it automatically plugs the 0 in so that people don't forget to turn stuff in. You turned yours in on paper to me, right?
No.
You did not.
I
Okay. Then,
I have it on paper if you want it, but I did.
no, so online's perfect, then they've changed something, cause it used to show up, until it's graded, it should show up as a dash. So it was. So you turned it in at 5 o'clock, so it will be, it's late, but it's not like a big deduction late. I think, see how it's kind of grayed out there?
Yeah,
I think that means it's not graded.
okay,
I used to show up as a dash, which was less confusing. But that just means I haven't graded that assignment yet.
okay.
And same for this last one, it
Oh,
says kind of grayed out,
Yeah, and for some reason,
or I might have graded yours, I graded some of these already.
well, for some reason. This didn't go through, so
Oh, okay,
I emailed you like as soon as I turned this in and saw that that didn't go through, I emailed you.
Okay.
A picture of it.
perfect. The other thing
Yeah.
you can do is you can actually just go back and add it as a comment.
Okay.
You can attach a file here, so if it doesn't upload because it doesn't always tell you when it finishes uploading, right? So if you hit submit, yeah, that happens.
Okay,
Yeah, so I did grade this one. I remember seeing that one there. So thanks for emailing me. I just haven't checked my email yet this morning,
no
so
problem, I just wanted to make sure.
I appreciate that.
Going through.
I'd rather you check and me be able to help you than you sit and panic internally.
Yeah.
I see if you can hit me in some other.
The worst is I naturally make that hand motion anyway, when I'm like, eh. It is interesting when you get a few more years further along and seeing what slang sticks around versus what disappears very quickly is not something you can really predict. Is what I've found so far. I would never have predicted yeeting to still be a word that people still use, but it's actually a useful way to describe what's going on. So yeeting's still around. 6'7" probably goes away pretty quick. No,
That's gonna be like 21, so it's.
Yeah.
Just hope she has this one.
Yeah.
One day. I thought she was too.
Well, I guess Craig won't do this, so she's not there.
That's why she got the 30%.
I know it's weird to do that, because when I'm working out and I'm counting my reps, I'm like, do work on 6, 7, 8, 9. It's always gonna be there.
The 3-year-old has picked up on it in my household. So you can't starting to count, so every single time it counts anything. 6, 7. All right, I realize we're still missing a good chunk of the class, but they can check the recording. We'll go ahead and jump back in here. So when we're talking about these periodic properties, there's basically a couple of really specific properties that we can estimate just by looking at the periodic table. Most obvious one is actually not an estimation at all, for the most part. Figuring out how many valence electrons something has is actually, once you understand what you're counting, the periodic table has that on there without actually needing the entire electron configuration, because top to bottom in the same group will always remain the same for electron. I can't say always. For the most part will be the same. So when we look at the periodic table, everything in this column has the same number of valence electrons. So the group, it's the old school way of saying column basically on the periodic table. I don't really like using group numbers that much because they actually are kind of weird, especially in the D block where they'll like group some things together. If you look at the way that old periodic tables count the columns, count the groups, it's like 1A, 2A, 3A, 4A, etc. But then down here you wind up with like 3B, and then these 3 together are all 3C, or maybe they're 4B. I don't even remember, because it makes more sense just to count your columns. So when you see group though, that's what it's talking about in chemistry. Group specifically means in the same column. Because things in the same column are going to tend to have the same properties. Right, so all of column 17, called the halogens, they all have similar properties in that they all have 7 valence electrons. They all are trying to gain 1 more electron to become more stable. Because if they all have 7 valence electrons, then they're all sitting with something P 5. Right, and so the most easiest way to get any of these things in column 17 more stable is to just gain 1 electron. So, and we see that for all of these columns, everything in column 1 has 1 valence electron. If it has 1 valence electron, what's the fastest way to make it more stable? Give it away. If we have 1 valence electron in this full column, they're all gonna try to give away 1 electron because then everything is either full or empty. And because everything in this first column is gonna, and its valence shell is gonna be XS1. Whatever row it is, S orbital with 1 electron in.
So.
Hydrogen, tricky. And actually helium too, for that matter. So hydrogen is unique in that because it only has an s orbital, it can actually become more stable by gaining an electron or losing an electron. So hydrogen really depends on what you put it. It'll either become more stable by becoming hydride. Hydrogen with a -1 charge is going to look like 1s2. But it can also be stable as a hydrogen ion with a plus charge, which would be 1s0. So hydrogen is unique in that basically it can lose all of its electrons. Everything else will always have some electrons. Hydrogen can lose all of its electrons and actually become more stable that way. And that's one of the reasons why that first row on the periodic table just looks a little bit different than everything. Some periodic tables will actually put hydrogen right here. Or even in right here and right here. Because it can either gain 1 more electron to become like helium, which matches these ones. Or it can lose 1 electron to become positive charge, which matches these ones. So hydrogen and helium both, you could actually put them into either column. Helium could also go right here. Because helium looks like 1s2, right? And everything else in this column is something s2. And so if you actually look at some older periodic tables, they'll actually put hydrogen and helium, and then over here they'll put hydrogen and helium. It's not wrong, it's just confusing unless you know what they're doing. Right, so if we're trying to count valence electrons, how many valence electrons would the aluminum have? We can write out the entire electron configuration, that's the foolproof way to do it. You can also just count what column it's in. Basically, you count the left-hand side, and you skip the d orbital and the f orbital, because those will never be part of the valence shell. So if we're talking about aluminum, sodium has got 1 valence electron, because it's because it's 3s1, magnesium is going to be 3s2, aluminum is going to be 3p1. So we're just counting across 1, 2, 3 valence electrons for aluminum. And boron, and for gallium, and for indium. Right, so if we understand the electron configuration, we can count valence electrons really fast. Now you don't even need to count it once you get used to it. I don't even count from the left over to figure out that chlorine has 7 valence electrons because I've done this long enough and I know where chlorine is on the periodic table. But while you're getting used to it, you just literally count from the left-hand side. What about valence electrons of ions? What happens when we change the number of electrons? So let's say, so we already looked at zinc and we found out that it was one S two, two S two, two P six, three S two, three P six, four S two, three D 10. So we said it had two valence electrons. What happens when it's in an ion? One S two, two S two, two P six, three S two, three P six. We're just leaving off the four S two, right? So we already did this one as an example. How many valence electrons does zinc have now? Yeah, I like this one as an example because the number of valence electrons changed. We lost it 2 electrons, but that doesn't mean it's got 0 valence electrons now. Because the valence level changed when we lost those 2 electrons. Our valence level was n equals 4 here, right? Remember our definition of valence means the highest occupied energy level. So when we get rid of those 2 electrons, the highest occupied level is now n equals 3. So it lost its 2 electrons and now it has 18 valence electrons. Which is weird. It lost 2 electrons, but now it has more valence electrons. Because the valence shell shifted. And so, the reason I bring this up is because at least when I was taking my classes, I noticed that periodic tables in biology classes, they kind of glossed over this. They didn't talk about electron configuration at all. They would just say things are more stable when they have 8 or 18 electrons in the outermost shell. But they wouldn't talk about why, or what is it about 8? How do you get 18 valence electrons in the outermost shell? Because everything else, when you fill it up to 8 valence electrons, that corresponds with filling a p orbital, right? So what the heck's going on with 18? You see 18 when you actually lose valence electrons. So things that have a positive charge can have 18 valence electrons because the valence shell shifts downwards. It's see, there's an analogy brewing in my mind. It's like opening up an 18 pack of soda when you have an almost empty 18 pack of soda sitting on top of it. As soon as you take out those 2 sodas on the top one and throw away that empty box, now the box that you have left has 18 in it again, right? By shifting downward in energy level, we actually have more electrons in the valence because the valence shell itself is not different. All right, so we spent a fair bit of time on valence electrons and electron configuration because it makes the rest of this table make more sense. So valence electrons, easy. Top to bottom is the same number. From left to right in one row, the periodic table, as you go from left to right, you're adding valence electrons. With the exception of what? With the exception of the D block. So basically, ignore the D block when it comes to counting valence electrons, and the F block for that matter. Let's talk about how big these atoms are, rather than how small they are. They're all very, very small. Atomic radius increases as you go down the periodic table. Within the same group, in the same column, when you go down a row, it gets bigger. Which makes sense when you think about it in terms of orbitals and energy levels, right? Every time we added another energy level. So if this was n equals 1, when we go to n equals 2, that was further away. So the radius is going to increase every time you add a new energy level. It just takes up more space. The one that's a little bit weird is when you go from left to right. When you go from left to right in the same row, things get smaller. When you're adding electrons into the same energy level, the size doesn't really change that much. Going back here, when we're adding electrons into 2s and 2p, those were all roughly the same distance from the nucleus. That's what makes them part of the same energy level. Every time we filled up an orbital and jumped to a new energy level, that makes it much bigger. But everything within the same energy level is close to the same size. Except if we actually start paying attention to it, as we add, what's changing? Besides the number of valence electrons, what's changing when you go from, say, boron to carbon? Number of protons. Boron has 5 protons versus carbon having 6 protons. What do protons do to electrons? They push them away or pull them in? They attract, right? So as you go from left to right in the same row, we're adding electrons into the same energy level so that the electrons are more or less the same spot, but we're adding more attractive force. Which means basically that you're going to pull all those electrons in tighter as you go from left to right. More protons means more attractive force, so everything gets sucked in a little bit more. Right, so it kind of is going to go a little bit like a typewriter. And then it's going to, as you go from left to right, it's going to go big, smaller, smaller, smaller. And then all of a sudden, when you get to the end of the energy level, it jumps up. Because that's going to correspond to filling up 2p, and then the next electron I add has to go into an entirely new energy level, which takes up more space all of a sudden. So right, if we're talking about students living in dorms on campus. Adding more students to our dorms doesn't really change the footprint, doesn't change how much space the dorms are taking up, right? Until we get to the point where now we have so much demand, we have to build a whole nother building. Going up a whole nother energy level is like adding a whole nother building. It's gonna all of a sudden jump up once you get to that point. And so, and we're gonna see something that looks, our overall trend is gonna be, it's getting smaller as you go from left to right, and then it jumps up, and then it's gonna get smaller as you go from left to right, and then it's gonna jump up. It's almost like a sawtooth pattern. But if we look at, say, the first element in every row versus potassium, as you go from top to bottom within the same row, they get bigger. And then within the same row, when they go from top to bottom in the same column, they get bigger. When you go from left to right in the same row, they're going to follow this trend. So what is this element going to be? We started this little series with lithium. The last element before we add a whole nother energy level is going to be neon. And then the last element here before we jump up to a whole nother energy level is going to be argon. And so we can estimate within each row pretty well what's bigger versus smaller. So I'm not gonna ask you to put numbers to these by memory. The way that I'll ask questions about this is gonna be like, out of these two elements, which one's bigger? Or here's three elements, arrange them from smallest to largest. It's always gonna be qualitative, because I'm not gonna make you memorize things like atomic radius of carbon. I don't know that. Why would I? I can look it up. But I do know that carbon is gonna be bigger than neon and smaller than lithium. Right, because carbon is gonna be right about there. In this chart. I think I have it with the actual. Don't have that. So your lab. Next week, whatever week we don't have Monday, so we're gonna do another, I'll have another week where we don't officially meet for lab. You're gonna basically, I'm gonna give you a table of data of different properties and make you make some of these graphs. So it'll be more practice using spreadsheets, except I'm gonna give you real data and say, hey, answer these questions about atomic radius, plot atomic radius versus atomic number. You're gonna get a graph that looks like that sawtooth pattern I just drew. And then you're gonna answer some questions and make some labels, basically just more practice with it. So it'll be another computational lab the next time we don't have an actual lab meeting. So we don't lose our spreadsheet skills that we just learned last week, right? All right. Spend enough time there. So here's some practice. Which element will have a larger atomic radius? I already answered the first one up there for you. But if you weren't feverishly writing that down everywhere that came out of my mouth, you might have to work your way back through that one. Same row on the periodic table. Further to the left is going to be bigger. Because it has fewer protons pulling its electrons in. Was that? Further to the right will be smaller. Further to the left will be larger. The other analogy you can do with these things when you go from left to right is it's like a person with a blanket. If somebody is really cold and they're a blanket hog, you give them a blanket on the couch, they pull the blanket in really tightly to themselves, right? You can't cover very much of the couch with a blanket if there's somebody that's pulling the blanket in really tightly. But if you're not pulling the blanket as tight, the same blanket can spread out over more of the couch. What about aluminum versus gallium? Gallium, it's below aluminum. They're both the same number of valence electrons. They're both in the same column. So we're not talking about left to right anymore. We're talking about up and down. So more energy levels means bigger. What about helium versus neon? Yeah, same logic, right? They're in the same column in the periodic table. Neon has more energy levels, neon's bigger. What about magnesium versus bromine? By far the trickiest one on there. We got both variables changing at the same time, right? Bromine is further to the right, which normally means smaller, but it's also lower on the periodic table, which means more energy levels, which usually means bigger. So we've got one trend saying bromine is smaller, the other trend says bromine is bigger. Which one's more important? It's actually in a gray area where I'd actually have to look it up. I don't actually know that when you have competing variables like this, you can't necessarily make those same generalizations because you don't know which of those variables is more important. So I put this one in here mainly as an example of a question I won't ask on a test. If you're gonna have both variables changing at the same time, I'll make sure that they're going the same direction, not counteracting each other. Because, like I said, I would want to look that one up. But if I said something like chlorine versus strontium. Well, chlorine's further to the right, which means smaller, right? And it's also further closer to the top, which means smaller. So both of our sets of logic say that the chlorine is smaller than the strontium. So we can say strontium is larger. But where they're competing like that, it's tough to say. Just so we can put an answer to it. Good old Wikipedia. So what's the atomic number for bromine? Of course, I picked one that doesn't even go there. So it's over here somewhere, right? Versus magnesium was what? 12. See how close that is? So this, like I said, this is an example of a question I would not ask on a test, or where I wouldn't expect you to be able to make that generalization. Because we'll actually get one where we can get a number to it, because now it's bothering me. So magnesium, empirical means measured, so we're going to use the empirical number for magnesium is 150 picometers versus bromine's 115. So magnesium is a little bit bigger than bromine, but they're close. All right. The next trend is called ionization energy. The ionization energy is not as general as it sounds. Ionization energy is not the energy to make an ion. Very specifically, the energy required to remove an electron. So it's the energy required to make a positive ion. Right, so energy, that's not an electron, to remove an electron. So as you go from top to bottom, those electrons that are in the higher energy levels, those are easier to pick off because they're further away from the nucleus. They're not being held on as tightly. Versus as you go from left to right across the row, it gets harder and harder to remove an electron because you've got more protons in the middle and you're getting closer and closer to having a full energy level. The closer you are to having a full energy level, the harder it is to take an electron away. And so think about when we talk about those d orbitals. We're never going to break up a full d orbital once it gets filled. But a d orbital with 9 electrons in it is going to try really hard to pull electrons in so it can finish that set, basically. If anybody does like blind boxes or anything like that, or collects sets of anything, when you're first collecting a set, it's really easy to get something you need for your set, right? You don't have to spend very much effort or thought on it because anything you get is likely to be new to you. However, the more and more you've collected of that set, the harder and harder it is to get that last one, right? which means you're more willing to pay more money to get that last one. You want it that much more when you're close to the full set. Electrons don't have actual like wants and needs, but the energy behaves in a similar way. It gets harder and harder to take an electron away from something that's almost a complete set, that's almost a full energy level. So ionization energy goes up when you go from left to right.
Is that a measure of force or charge required to pull it away?
So force, when you take physics, that'll make more sense, but force and energy are not the same thing. Force is part of energy. You have to, I think it's a force times a distance is an energy unit. So force is how hard you're pushing on something. The total amount of energy it takes would be, okay, I had to put this much force into it for 10 meters is your total amount of energy. So it's a little bit different, but so we can think of it more in this case as being more like the magnetic attraction. It gets harder and harder to take the electron away, the more protons you get in that same energy level. So this one's also going to have a plot that looks kind of like a sawtooth, except it's going to be backwards. So for atomic radius, we said it looks kind of like this, right? That's terrible. But it gets the point across. For ionization energy, it's going to be the opposite. It's going to go up from left to right, and then it's going to drop. And then it's going to go up again, and then it's going to drop. Right? What's going to be in the second row of the periodic table? What's going to be the hardest thing to take an electron away from? Neon's the noble gas. It already has a full energy level, right? So it's going to be really hard to take an electron away. Lithium should be the easiest.
Yes, realize that.
Okay, so lithium should have the lowest ionization energy, and neon should have the highest ionization energy. All right. Last variable to consider. Just because this is another one that I'm not going to ask you about specifically because it's not as well defined as the other terms. It gets a little bit fuzzy. Metallic character is basically a way of saying how metal something is. Not in the musical sense, but in the metal sense. But it's tricky because metallic character is made up of several different variables. They all kind of combined to give it an overall metallicity score. So I don't particularly like it, but it does show up in textbooks, so I want you to have seen it. Basically, things get more metal the more conductive they are, and the more malleable they are. So metal character is a combination of conductivity, so electrical conductivity, but also thermal conductivity. Metals that are really good electrical conductors are also really good at conducting heat, typically. But it also is a measure of ductility. Something is ductile when you can grab it and pull it and turn it into like a string shape. So if you think about taking, I don't know, a piece of chewing gum, you grab both sides of your piece of chewing gum and you pull it, it makes a nice long pull, right? That substance is very ductile that way because you can take it and turn it into this big long strand by just pulling on both sides. So the cheese is the same way, right? Especially melted cheese. And also the other term is malleability. What is malleability? That's an L. What does malleable mean?
You can change its shape by applying pressure.
Change its shape, that's a really good definition, change its shape by applying pressure. Malleable actually comes from the Latin word mallus, which means able to be hammered. Mallus is the Latin word for a hammer. So malleable means you can literally hit it with a hammer and make it into a flat shape. Metals tend to be very malleable, even if we think of them being very hard and rigid. If you just sit there with a hammer and you hammer on a piece of metal, you can flatten it out. The more metallic something is, the more malleable it is. There's actually a lot of good heavy metal type album names, band names you can come up with based on that. There's also a really famous document from the Dark Ages called Malleus Maleficarum, which translates to the Hammer of Witches, which was what the Inquisition used as their like guidebook during the Dark Ages to determine if someone was a witch, and how to punish them, was found in this textbook put out by the Vatican called the Malleus Maleficarum, which I've always thought would be a good name for a metal band. All right, so with all this in mind, how do we judge anything by just one metallic character? It's kind of hard, which is, like I said, why I don't like this definition that much. Things that have really low ionization energy tend to be better electrical and thermal conductors, though. So basically, what part of the periodic table, what corner of the periodic table has the lowest ionization energy? So when you go from top to bottom, ionization energy goes down because you're getting further and further away from the nucleus, right? So further to the left is low ionization energy, and further down is low ionization energy. So the bottom left corner is our most metallic elements, which is not necessarily the ones you would expect, because what do you think of when you think about metal? Iron, gold, copper. Those are all the other direction from that. So why don't we think of things like potassium as being a good metal? Turns out potassium actually does have these properties, but it's also incredibly unstable in the presence of oxygen. So metallic potassium is actually so malleable, you can actually, it's like Play-Doh. You can squeeze it with your fingers in gloves, and you can actually get it to deform, like literally like squeezing Play-Doh. It's very malleable, it's very conductive, it has a high degree of ductility. We don't use it as a metal very often though, just because if you expose it to oxygen, it catches fire and burns. Because it's so easily oxidized when you expose it to oxygen. So what we think of as being good metals, like copper and gold and iron, are actually some of the worst metals by this measure, but they tend to be very stable in oxygen. So we find them as metals a lot more often in nature. The reason that gold gets used in wiring a lot, especially for electronics and things like that, is not necessarily because it's the best conductor. It is a pretty good conductor, but also because it's really easy to put it in the right shape, and it's never going to oxidize in the presence of oxygen. So it basically means that it'll last forever as wiring, as opposed to aluminum. Has anybody ever done any electrical work? I worked on a house before. Anybody ever worked on a house that had aluminum wiring? We don't even have them here because in the West Coast, we weren't even building houses up here in Tahoe when aluminum wiring was still a thing, because aluminum oxidizes so easily. But if you go back east to houses built in the 1800s, you can find a lot of aluminum wiring or knob and tube wiring that we don't use anymore. Because those metals are just not ideal. I think Nava tube actually uses copper, but it puts it into like a ceramic pipe instead of like a traditional plastic, not traditional, a modern plastic wrapping. All right. Last 10 minutes because I need to get through these slides and they don't fit anywhere else. So this is just a couple more vocab terms. We've been kind of using some of these terms already, so this should be pretty easy. When we talk about different types of matter, we also want to be able to classify them. We already started talking about, okay, different types of elements. We can classify different types of elements based on how many protons they have. But it turns out if we're talking about pure substances, there's more to it than just how many protons are in the nucleus. All right, so if we're talking about elements, an element is defined by number of protons. But you can have a pure substance that's made up of more than one element. How does that work? Well, pure elements all make sense from a macroscopic point of view. A pure element just means that every atom is identical to every other atom. So if I looked at an aluminum can, if I grabbed an atom at random from the aluminum in an aluminum can, it's aluminum, 100%. Every atom is identical, and every atom has the same number of protons. Copper, even helium, right? If I have a gas, if it's a pure element, every single atom I could grab is still going to be the same element with the same number of protons. So what's different about compounds is that compounds are made of multiple elements, but they're always combined the same way, in the same ratio. So water is the classic example because everybody knows the formula for water already, right? Water is H2O. Water is H2O because these atoms are always connected in the same way. You can't change the ratio of hydrogen to oxygen and still have it be water. If you add extra oxygens into your water, it's no longer pure water. Right, so compounds are made up of multiple elements, but they're always combined in the same whole number ratio. Right, so if water is H2O versus hydrogen peroxide is H2O2. Pure hydrogen peroxide is its own compound. It's still just made out of oxygen and hydrogen, but now it's in a 2-to-2 ratio versus a 2-to-1 ratio. And so that's what differentiates between these two compounds, is that ratio. The fact that these atoms, even though they're still hydrogen and oxygen, don't react the same way as water atoms do, or water molecules do. Sodium chloride is another example. Sodium and chloride have to occur at the same ratio. You can't have low sodium salt. Because salt, like table salt, is defined as being sodium chloride, which is always in the same ratio. Right? So what about something where we can have different amounts? Like if you look really closely on this bottle, it actually says 3% on it. Can you get hydrogen peroxide from the grocery store in different strengths? Yes. Turns out you get, maybe not at the grocery store, you might have to go to other sources, but you can get 9% hydrogen peroxide, you can get 30% hydrogen peroxide. Because what's in this bottle is not pure hydrogen peroxide. It's a mixture of two compounds. Any guess what the other compound is that we mix hydrogen peroxide with? Water, we put it in water. We don't want pure hydrogen peroxide because it's too nasty. Even 30% hydrogen peroxide, if you let it sit, it will build up in excess of hydrogen gas and oxygen gas inside the container, becoming very, very flammable and explosive without even opening it over time. So we basically cut it with water, which makes it not a pure substance anymore. A pure substance means that all the atoms are always combined the same way. If we have more than one different ratio that you can have, it's not a pure substance anymore, it's a mixture. So a mixture is a combination of elements or compounds where the components can be mixed together in different ratios. So the fact that hydrogen peroxide and water, we can get that in 3%, 9%, 30%, tells us it's a mixture. Is all salt water the same saltiness? No. If you get salt water from the Dead Sea in the Middle East versus if you get salt water from Salt Lake versus ocean water, they're all different levels of salinity. I think the saltiest water on Earth is actually in Antarctica. There are some sub ice pockets, lakes that are so brackish that it basically grows salt crystals around the outside. And it's like almost painfully salty. The fact that you can have different degrees of saltiness tells us it's a mixture. We don't have to add the same ratio of salt to water every time. And you don't need to get out a scale to measure. If you're cooking pasta and you want to salt the pasta water, you don't get out a scale and very precisely weigh out, I'm going to put in 1.52 grams of salt to salt my pasta water, right? You just grab a handful of salt and you throw it in. Because it's a mixture, you just want to get it close. It doesn't have to be as precise. The other thing about mixtures, and this is not always obvious, but mixtures, you can physically separate the components. Meaning you can take apart, if you have salt water, you can remove the salt and the water and re-separate them pretty easily. How do you do that? Boil it off. You boil the water evaporates off and the salt's left behind, right? Pretty easy way to separate those two things. If I told you to separate the hydrogen from oxygen in water, would that be as easy to do? So that's what's meant by physically separating components. You can't physically separate the components in a compound. You can't separate the chloride from the sodium in salt. And mixtures can be made up of more than one element. Compounds, both. Our atmosphere is a mixture. We care about our atmosphere, care about one compound in our atmosphere more than the others. What do we care about most in our atmosphere? Oxygen, because being organisms that depend on breathing oxygen to survive, that's naturally what we're focused on. But there's all this other stuff in there too. There's nitrogen, there's water, there's CO2, there's methane, there's argon, a little bit of helium. All of that's present in our atmosphere, which makes our atmosphere a mixture. Anybody do any scuba diving? A little bit. What happens when you have to go down lower than 100 feet?
You gotta, wait around for a while so that you don't get the bends.
You gotta wait around for a while, and if you wanna go like really deep, you need different tanks, right? Is it NOx? What do they call it? What is the mixture that they use for really deep water? I can't remember off the top. You don't remember? There's basically a special blend of gases. You need a different mixture of oxygen to nitrogen if you're gonna go deeper than, I think it's 150 feet, maybe 200 feet. If you're gonna go past that underwater, you actually need a mixture that has less nitrogen in it so that you don't get the bends when you come back out. That's more oxygen dense and has other stuff in it that's less likely to cause problems when you come back up. The fact that the nitrogen and the oxygen can be present in different ratios tells us it's a mixture. All right. Last two terms. Heterogeneous versus homogeneous. You've probably heard these terms before. Kind of why I'm going fast with some of these, because a lot of these are terms that have show up other places. Homogeneous just means it's uniform. It's well mixed. If you take a sample from the top, it's pretty similar to the sample that's at the bottom. Versus heterogeneous means unevenly mixed. So if you put a sugar cube in your cup of tea and you just let it sit there without mixing, is it gonna be homogeneous or heterogeneous? Yeah, because if you get that last sip of tea, it's really sugary, right? The sugar is not, if it's not well mixed, the sugar's all gonna sit at the bottom. And the sample at the bottom is not gonna be the same as the sample at the top. Right, so now that we've defined those terms, here's some examples. We'll start with this. We'll talk about physical change versus chemical change on Wednesday. All right. Thanks, everybody. I'll see half of you for lab in a little bit. Everybody else will see you Wednesday.
Periodic things, right?
Yeah, quiz is on Wednesday. Thanks for reminding. Quiz Wednesday for the periodic table.
Well,